as soon as his slides come up. All right, over to you, Amit.
Good morning. I would like to thank the organizers for giving me the opportunity to present our work. Let me start by introducing my great, wonderful collaborators. This is Barak Gabay, who is a PhD student at Harvard, and this is Deliang Zhang, who is postdoc at Tel Aviv University. Now, this talk is based on 3 papers, 1 short that came out and 2 others that will come up this year. So let me start from a short motivation. Chern-Simons possesses a non-perturbative level-rank duality. Now, once we couple Chern-Simons theory to matter, this duality is expected to extend to a duality between the theory coupled to boson and the theory coupled to fermion. Now, this is something that is very hard to prove because this is non-perturbative. It maps the weak coupling of one side to the strong coupling limit of the other side. Now, what I mean by expected is that by now we have very strong evidence for it, starting with, for example, the correlation function of local operators, the spectrum of monopole and baryon operators, thermal free energies, S matrices, and sometimes relating non-supersymmetric dualities to well-established supersymmetric ones. And here I gathered together many people that work on this duality, and I'm sure I have forgotten some, so please forgive me. Actually, the first clue that that this duality should extend to a duality between fermion and boson comes from studying Chern-Simons itself. We started from the famous paper of Witten. Suppose you consider a closed Wilson loop in Chern-Simons theory. Okay? If you want, this is a topological theory, and if you want to to extend the definition of this operator in the quantum level such that it preserves its topological nature, you have to introduce what is called a framing vector. This is a small normal vector along any point along the loop that is used to define this operator at the quantum level. Now, suppose you compute the expectation value of such a simple loop, what you find is the following expression. So here in this talk, I will only consider SUN or UN gauge group and only study the theory at the 't large n limit. The 't large n limit is the limit where the rank of the gauge group is sent to infinity with the ratio lambda, which is the n over the level of Chern-Simons, kept fixed. Okay? So this ratio runs between 0 and 1 or minus 1, depending on the sign of the level. 0 is the weak coupling limit, and 1 is the maximal coupling. So when one computes the expectation value of such an unknown Wilson loop, find some function of the 't coupling, what I want to focus on is this phase factor here. I have e to the I pi lambda times f, where f is called the self-linking number. It's kind of the number of times the framing vector runs around the loop as you go around. For example, in this picture, it is equal to 1. Therefore, you expect that once you take such a framed loop and couple it to some source, some field in the fundamental representation, the same phase-dependent factor would now turn bosons into fermions and the other way around. Meaning that if we started with a boson at lambda equal to 0, in the maximal coupling with lambda equal to 1, when we turn it around, it will pick the spin 1/2 and the other way around. In this talk, we will prove this in the planar limit. So let me be a bit more precise about the plan of the talk. I'm going to study 3-dimensional conformal field theory that are obtained by taking Chern-Simons theory and couple it to boson or fermion matter in the fundamental representation. For boson, for example, you have to tune some coupling to stay at the conformal fixed point. So I study these 2 theories, or the theories that you get from these by deforming them by a double trace deformation with respect to what is called J0, which is the biscalar or bifermion. This is also equivalent to doing Legendre transform with respect to these 2 double trace currents. Let me what we will focus on is what are the most fundamental operators in such a gauge theory when you have matter in the fundamental representation. And these are line operators, such as Wilson loop, stretched between a fundamental and an anti-fundamental operators. Let me start with some Largen counting. So if we just consider a closed Wilson loop, the matter, because there is some finite number, here one fundamental, finite number of flavors, the matter only contributed order 1 over n to the expectation value of closed Wilson loop. However, if you study the expectation value of what I call these mesonic line operators that stretch between a fundamental and an anti-fundamental operator, the matter contributes already at leading order. On the other hand, the double trace deformation contributed 1 over n squared to the expectation value of a closed Wilson loop, at 1 over n to the expectation value of these mesonic line operators, and only start contributing order 1 to the connected piece of correlation function of mesonic line operators. Therefore, in the main of this talk, we will focus on the expectation value of these mesonic line operators, and it wouldn't matter if we are describing any of these two theories or their double trace deformation. Okay. I'll comment at the end where it enters when we study the connected correlation function between them. So, due to time, let me start by just summarize the result, and then as time permits, I'll go and elaborate on them and how we obtain them. So the first thing, if you consider just a naive line operator, for example, a Wilson line in the bosonic theory, such a line operator will experience RG flow on the line. So the first thing we have done is classified what are the fixed points of such flows, what are the conformal line operators in these theories. The next thing we classified, what are the operators such lines can handle, what are the boundary operators, and what operators can live on the line. Okay? Called boundary and bulk operators on the line. Everything done as finite value of the Tooth coupling. Next thing, what we have shown is that these line operators satisfy a sort of a loop equation. What it tells you, we call it an evolution equation. If you deform a bit the path, what you get is a factorized product of two mesonic line operators. And lastly, what we've shown is that the knowledge of the boundary operator, the scaling dimension, and this operator equation, the evolution equation, is sufficient by a bootstrap to uniquely fix the expectation value of these line operators along arbitrary smooth path. Okay. So, finally, we've shown that the conformal line operators in the theory coupled to bosons and in the theory coupled to fermions have the same set of conformal line operators. They satisfy the same evolution equation, and have the same spectrum of boundary operators. Therefore, they also have the same expectation values. To demonstrate that, for example, we've computed I would say, the first non-trivial piece when you compute the dependence on the shape of such a mesonic line operator, which is the two-point function of the displacement operator. The displacement operator that I noted here by D is the operator that displaces the path a bit in an orthogonal direction. So here I wrote mesonic straight line operators between two boundary operators, and these will be the boundary operators of a minimal dimension and opposite transverse spin. And here there are two deformation operators. By conformal symmetry, the expectation value of this object normalized by the one without the displacement operator takes the following form. Here we have a conformal cross ratio of this 4 point to the power 2 times the dimension of the boundary operator, 1 over x to the 4. This is because we see the displacement operator as dimension 2. And here there is no trivial function of the coupling, or no trivial function also of the dimension of the boundary operators. And what we get by the bootstrap is this non-trivial function where the dependence on this dimension on the Tooth coupling depends on which line operators you are using, or whether you use the bosonic or the fermionic description. Okay. So the plan of the talk is the following. I'll start by describing the bosonic theory, then I'll shortly describe the fermionic dual, and as time permits, I'll talk a bit about the bootstrap, even though this was the main part of this work. To set the ground, I'll just assume that the level in the bosonic theory is positive, meaning the tooth coupling in the bosonic theory run between the weak coupling, which is 0, and the maximal coupling, which is 1, while the dual one is run between 0 and -1. The other option is just related to this by parity. And warning, I'll just mainly present the main ideas, but with no details. So let's start with line operators in the bosonic theory. If you study in the bosonic theory, the naive thing to start with is just a standard Wilson line. However, just a Wilson line turns out to have a non-trivial beta function for the biscalar adjoint. This is fundamental, anti-fundamental scalars that are not contracted together, but contracted with the line. This is an operator that lives on the line. At tree level, it has dimension 1, because the scalar has dimension 1/2, and at loop level, it turns out to have a non-trivial beta function. At the fixed point of this flow on the line, we find two conformal line operators. This is described by W here. Here C is arbitrary smooth path, and N is the framing vector that's used to define this operator at the quantum level. Now we find here that this biscalar have to condensate in the exponent, and the coefficient up to this factor is given by this alpha that is plus or minus 1. So we have two different conformal line operators. Turns out that the conformal line operators with alpha equal to 1 is a stable fixed point on the line, where the one with alpha equal to -1 is an unstable fixed point that if you change a bit the coefficient of the biscalar can generate a flow to the stable one or to an almost trivial one. Okay. There are also other conformal line operators, ones with degrees of freedom on the line and ones that are non-unitary that I don't have time to describe. So we'll focus on these two in this talk. What are the mesonic line operators? The mesonic line operators are obtained by taking such a conformal line operator along a smooth path and letting it stretch between a fundamental and anti-fundamental boundary operators that I call here the right and the left operators. Okay. The operators that live on the line in the planar limit, they're all factorized into product of two of these, the right, the fundamental, and the anti-fundamental, just like the biscalar in the exponent before. Therefore, by classifying the boundary operator, we automatically also classify all the bulk operators. It turns out that to classify the boundary operators, they are classified by two quantum numbers. One is their conformal dimension, and the other is their transverse spin in the plane perpendicular to the line. They're always in 3 dimensions. Okay. For example, if you're considering the scalar theory at tree level, these boundary operators, if you look on the fundamental side, are just a scalar and its derivative. They can be longitudinal derivative along the third direction, this is the direction I put the line, and transverse derivative with plus or with positive or negative transverse spin. Their dimension at the tree level is just the 1/2 dimension of the scalar plus the total number of derivatives. However, at loop level, they get anomalous dimensions. The operator with no longitudinal derivative turn out to be also primaries. If you have a straight Wilson line, it preserves an SL2 cross U1 conformal symmetry, and the operator with no longitudinal derivatives are primaries of this SL2. Now, here's the spectrum that we find. Find that the spin of the boundary operator gets an anomalous piece, which is equal to plus or minus lambda over 2. Okay. Well, the dimension also gets an anomalous dimension, which is related to the spin in this simple way. In other words, both the dimension and the spin of the boundary operator get an anomalous piece, which is equal to lambda over 2. Okay. Operators with the same anomalous dimension can be related to each other, what you call path derivative. This is like the analog of a covariant derivative. So the conclusion of that relation is that it's enough to consider 4 operators that are the one on the bottom of the tower of operators that we have, and all the rest of them can be obtained by these 4 by taking covariant or path derivatives. Okay? These 2, for example, have opposite anomalous dimension and opposite spin, and all the rest are obtained by these derivatives. Now, how we derive this spectrum? So first, we did all-loop computation and derive it just explicitly. This is a long story. This is one of the paper that is upcoming, and I don't have time to describe unless there will be questions. Okay? So this is just the result on explicit computation. One other way to check it or to derive it is that you see here that the relation between the anomalous dimension and the anomalous spin reminds one of a BPS relation, and this is not an accident. We can lift these operators to an operator in a supersymmetric theory and obtain this relation and show that it's the same as in the non-supersymmetric ones. So this spectrum basically confirms the expectation that once we couple this line operator to a boundary operator in the fundamental, and we turn on the Chern-Simons coupling, it dynamically changes fermion into bosons and boson back to fermions. This is because the spin, if you started with spin that is integer, at the maximal coupling, it will be half integer and the other way around. We can ask, what is the operator of minimal dimension on the line? The operator with minimal dimension of the line is exactly the same biscalar that we had in the exponent. Its dimension is just the sum of the dimension of the 2 pieces. And because they have, each one of them is dimension 1/2 plus lambda over 2, the total dimension is 1 plus lambda, which is bigger than 1, meaning that this is an irrelevant perturbation of the line, and therefore the operator with alpha equal to 1 is a stable fixed point of the RG flow on the line. Next, we would like to understand the dependence of this operator on the shape of the line. So for example, if you take this conformal line operator with 2 scalars at the endpoint, just by conformal symmetry, it's expected to take the following form, where the distance to the power 1 plus lambda, this is account for the conformal dimension of the 2 boundary operators. We have here the value of the framing vectors at the 2 ends. This is account for the anomalous or the transverse spin, and here we have a conformal invariant function of the path that we would like to understand. Now, in order to understand that, what we ask is what happens when you take such a smooth path and deform it a bit. And when you deform it a bit, this is the definition of the displacement operator. This is a local operator on the line that displaces the line in an orthogonal direction, V. V is some small orthogonal deformation of the path X. Now, if we look on the spectrum of operators, it turns out that there is a unique operator that is the displacement operator, and it's made of a product of a right and left operator, and it's chiral. It's different from the plus and minus transverse derivative. Here the spin is coupled on the right with the left boundary operator. Here the spin is coupled on the left with the right boundary operator. Okay? Note that the dimension of the displacement operator is just fixed by this equation to have dimension 2 to account for the dimension of dx and v, and spin 1 because of the spin of v. Here, when you look on this product, it's a very funny story because each one of them have both anomalous dimension and anomalous spin, but they're exactly opposite and cancel each other in this combination. So this displacement operator was also computed by an explicit Schwinger-Dyson-like deformation of the line. What it tells us now, therefore, that under a smooth deformation, we have to insert the displacement operator and the expectation value of this operator factorize into right and left operators. There is also a boundary analog operator equation. What happens if you try to reduce the spin of the boundary? There is a unique operator there that have the right dimension and spin with a priori an undetermined coefficient. This is the quantum extension of the equation of motion for the scalar, box phi equal to 0. And the bootstrap tells us that in our normalization, this factor is just equal to 1/2. In other words, doesn't get loop corrected. We have repeated the same story for the operator with alpha equal to -1. The spectrum turned out to be the same, except the two scalar operators that now have the opposite anomalous dimension and anomalous spin. So again, we have 4 towers of hope operator built upon these 4. But the difference now is that the operator with minimal dimension, again, the biscalar, is dimension 1 minus lambda because the anomalous dimension is flipped. And therefore, this is an unstable fixed point that takes us to the other one. Let me now go quickly for the fermionic theory. The basic idea that we repeat the same story there. In the fermionic theory, just the standard Wilson line is a good conformal line operators. And we repeated the same explicit computation. And what we find is exactly match both for the spectrum and the evolution equation with the operator with alpha equal to 1. So for example, the scalar in the bosonic theory mapped to one of the components of the fermion in the fermionic theory, and the other component is mapped to the plus derivative of the scalar. And similarly for the anti-fundamental on the other side. We find also the fermionic dual of the alpha equal to -1, the unstable conformal line operators. But this one is turned out to be a bit exotic. Because this one, if you take the lambda to be the coupling to be maximal, the dimension of the boundary operator goes to 0. It turned out that this operator is a fundamental condensate operator in the exponent. In other words, when you expand it, it has pieces of the line that have a Wilson line, like between fundamental and anti-fundamental, and the pieces that are almost empty. They have some spin transport between them. But this operator is not something that I would naively imagine exists, but it turned out to be just a dual of the alpha equal to -1. You can repeat the explicit computation, and everything matches. For example, again, here we have the scalar. It's dual to the empty end here, while the other operator is the derivative of the scalar, and move to one of the derivatives of the fermion at the endpoint. Running out of time, so let me now shortly describe the bootstrap, and then I'll conclude. So the basic idea of the bootstrap is to show that the evolution equation, this operator loop-like equation, and the knowledge of the spectrum of boundary operators are sufficient to fix the expectation values of this object. The way we did, we started from a straight line. From a straight line, the expectation value is just fixed by conformal symmetry, and then we deformed it smoothly. Now, when we deform it smoothly, at any order, we included all relevant or marginal operator on the line and on the boundary. Then we have to fix their coefficients. To fix their coefficients, we have to pick a regularization scheme. And the first thing we demand is the conformality of the line. But that turned out to be consistent with the spectrum of boundary operators. This turned out to be not enough. We have to also consider that under any smooth deformation of the line, if on top of that you do another small deformation, the line is still conformal, and this turned out to be enough to fix all the coefficients in the expansion. So, for example, in this way, we obtained this two-point function of the displacement operator that I alluded for before, where here you see the dimension of this boundary operators is one of the operators in the bottom of the 4 towers, which has dimension 1 plus lambda or 3 minus lambda over 2. We go to future directions. So here, basically establish the duality at the level of the expectation value of these mesonic line operators. But if you want to complete the derivation of the duality between the bosonic and the fermionic theory, you also have to match the connected piece of the correlation function between mesonic line operators, or between them and the local operators. Okay. Here what we expect is that if you add also the known spectrum of single trace operator, this would be sufficient, and this is something we are working on. Another future direction, here I show that the spectrum and the evolution equation are sufficient to determine the expectation value, but we haven't computed it explicitly. We only computed it explicitly at some order in perturbation theory. It would be nice to find an explicit solution to these equations. And finally, this was actually our original motivation for this project. We would like to derive the holographic dual of these theories. These theories are expected to be dual to a parity breaking version of Vasiliev theory in ADS. And we think that these are the essential step in order to derive the duality. This is something also that we are working on. Thank you.
We have time for some questions. Yes.
Something strange.
Thank you. So at a certain point you mentioned supersymmetry, but you do not have supersymmetry in your theory. Not yet. I'm here. Hello? Okay. So my question is, what happens is if you really look at some supersymmetry n equal to 2, n equal to 4, n equal to 6, 8, whatever, Chern-Simons-Matter theories in 3 dimensions. I mean, this comes out to be a self-duality or something like that?
Yes. This is a self-duality in this case.
But I have a related question, because when you consider BPS Wilson loops, some kinds of fermionic BPS Wilson loops do have a phase factor in front, which is not only due to framing, it is also due to some extra contribution from matter sector. So my question is whether this might spoil your reasoning, or...
If it's there, it should come about from the equation. So first, if you consider the n equal to 2 theory, for example, at the planar limit, the expectation value of the operator I talked about are the same in the non-supersymmetric one and in the supersymmetric one. Now, everything follows from these equations. For example, something I haven't talked about, but you can reproduce perturbation theory from the equations, from this loop equation, and that's enough, actually.
A kind of similar question. Can you, so you said you can uplift to supersymmetric theory and more or less it is the same and this other stuff decouples. So can you reproduce your result from some localization type of calculation?
If you can compare this result to results from localization, that is the question. I don't know how to localize this type of operators in the supersymmetric theory. That's what you're asking. Note that here we kept the shape of the line arbitrary but smooth. Okay? So when you do that in the supersymmetric case, you usually preserve supersymmetry locally on the line. But once you let it wind around, you break all supersymmetry.
Are there any more questions? Yeah.
I just have a naive question. So in your bootstrap argument, you work to all orders in conformal perturbation theory. How do you know that there aren't non-perturbative corrections that mess up the argument?
Non-perturbative in conformal perturbation theory?
Yes.
We were doing deformation of the path.
Yeah, you're deforming the line, right? So
we're only considering smooth deformations. So for smooth deformation, I would not expect. This is not perturbation theory in the tooth coupling.
Yeah,
this is perturbation theory in the shape of the line.
Yeah.
Yeah.
I mean, maybe there aren't any. I don't know. It seemed like a question.
Probably a convergent series.
Yeah, I guess maybe that, right. I guess that's the way to ask it. Yeah, it's the series convergent.
Another check is that the bootstrap gave this two-point function of the displacement operator, which we also obtained by explicit all-loop resummation, and they match. Okay.
Any more questions? Okay, it seems that we are on time, so let's thank Amit again for a wonderful...